Okay, so that puts us in an excellent position to have a look at the other major statistical inference technique, and that is hypothesis testing. So, before we switch to the slides, I would like to have a little talk about it generally, and then we will be able to sort of catch up in the slides. Now, first thing I need to say about today's work is that conceptually, I think it's even more tricky than what we did with estimation. It is going to come from our Topic 7 theory once again, and there's also going to be a link between today's new work and the estimation work that we covered last week. But because hypothesis testing is such an important statistical inference procedure, we need to make sure we really understand what it's all about. That's going to take us most of today. Once we've got that under control, we can do some practical problems, put in some numbers, come up with some answers, see some different variations on this technique. But the first, most critical thing is to understand what we're trying to achieve here. So I'm going to try and lead you through it step by step. Make notes, but try to listen as carefully as you can. And we will link it back to something that's sort of more everyday life and less statistical, so hopefully that will help. Okay, we know statistical inference is all about trying to say something about the population using our sample. Rather than saying, okay, I take a sample, I come up with my sample statistics, such as sample mean, I expand on it to come up with my confidence interval. We're going to take a different approach to our analysis today. Ultimately, it's still statistical inference. We're still going to use our sample to say something about the population, but we're just taking a different perspective in how we look at all the information and what we're trying to achieve. So this is how it works. You start with a claim about the population. We make claims about populations all the time in everyday life, and we don't really think about the fact that we do it. I know this is a little bit probably showing my age. I don't think it's been on TV for a little while, but it used to be quite famous to have those sort of toothpaste ads on TV where there'd be a dentist standing in front of a mirror but you wouldn't see his face, and they would say something like 4 out of 5 dentists recommend this toothpaste, or 9 out of 10 dentists recommend this toothpaste. It's a claim. So they're making a claim, and when they make that claim, they want you to think that that claim is with respect to all dentists. When they say 4 out of 5 dentists recommend this toothpaste, they don't want you to think, oh, well, that was 4 out of 5 in the sample of 50 dentists that they spoke to. They want you to think 4 out of 5 is with respect to all dentists, the population of dentists. When there's ads on TV for batteries, and they say, you know, ours last longer than any other on the market. Maybe in the sample, but they're stating that to you, that claim, as if it's with respect to the population. And remember, that's really what we want to talk about. We don't want to talk about individual samples. We want to analyse populations. We want to generalise results. So in today's work, we're actually going to start with the claim. And that claim, importantly, is with respect to the population. So you say something about the population. You make a claim. Now notice, I've used the word claim. I'm not asking a question. I'm not saying, do 4 out of 5 dentists recommend XYZ toothpaste. I'm not asking you a question. I'm stating something. I'm making a claim. Another way we could refer to that is I'm presenting you with a hypothesis, a statement. Most certainly not a question. Now, just a little fine point in terms of the practical work we're going to go on to today. 4 out of 5 dentists. 4 out of 5 is 80%. So, in fact, here, this example I'm showing you is a claim with respect to population proportion pi, and I'm claiming that that population proportion pi is 0.8. So, even though it starts off looking very everyday life, very wordy, it does translate into something mathematical. Okay, so I start with the claim. Can I prove it? Well, never 100%. The only way to be 100% would be to ask every dentist, i.e. to survey the entire population, which for all the practical reasons that we've talked about previously during the semester is most likely not going to be the case. If you've got population data, well, you don't even need to think about statistical inference because you can just analyse the population data and your results are population results. Statistical inference is only relevant when we need to use a sample. But the reality is, in real life, I want to make claims about populations. I'm never going to be 100%, but what can I do? I make the claim about the population. I can then take a sample and use my sample as evidence to either support or reject that claim. So if I'm claiming that 4 out of 5 dentists recommend XYZ toothpaste, and you then go and survey 50 dentists, and you find that the sample proportion is in fact 20%, 20% would be a long way from 80%, and certainly that sample would be suggesting that my claim is false. So we start with the claim, take a sample, and we're going to use that sample as evidence to come up with a conclusion about our claim, to either support it or reject it. That's basically what we're going to do today. And how we do that? Well, we know that when we take a sample there's uncertainty, but we know there's a link between population distributions and sampling distributions. So once again, we can just use all that theory, all that knowledge about how populations and samples are related to come up with a technique to do exactly what we're saying we want to do here. And it's known as a hypothesis test. And it's going to be quite formal, and it's going to require certain things be done, so it's presented in a very sort of standardised format, so that when you make a claim and you present this analysis and then have a conclusion, that people know exactly the technique that's been used. It's not something where you get creative. It's very strict and formal. So part of our job today is going to be to learn, once we're comfortable with that idea of what we're trying to achieve, to actually put it into practice and to be very formal about this test. Now, part of being formal means that we have to be very clear about the claim we're making. Claim, and I said we could also in fact call a claim a hypothesis. And in fact what we're going to do is we're going to cover all the possibilities. So we're going to have a hypothesis known as the null hypothesis, and the notation is just going to be H0. And for example, our null hypothesis might be that our population proportion pi is equal to 0.8. And pretty much this null hypothesis is going to be considered the status quo, the sort of starting position, and then you're interested in whether or not that position continues or whether there's some change. So you have this null hypothesis, but then you also set up the alternative hypothesis, which is H1 or HA, it doesn't matter which subscript you use, they both represent the alternative hypothesis, it's just personal preference. And the idea is that that's the opposite to the null. So in our case it would be that pi is not equal to 0.8. So we think of the alternative hypothesis as the hypothesis of change. And the idea is that there is some status quo, there is some existing position. So maybe in the past it was quite clearly established that, 4 out of 5 dentists recommend XYZ toothpaste. We're a new company, we think that that result is no longer valid, so we want to do some testing. So there is that status quo claim that the proportion is 80%. We think that it's changed and it's no longer 80%, so we could run a hypothesis test, taking a sample to use as evidence in this test. The null is the status quo, the alternative is the hypothesis of change. And basically the way it's going to work, because that null hypothesis is the status quo, the sort of existing position, when you use the theory, you're in fact going to assume that the null is true unless the evidence is strong enough to prove otherwise. Now, that idea takes a little bit of getting used to. So I want to give you something to think about that is maybe a little bit easier to contemplate because it's not really mathematical.